Hi, gang. We're going to go ahead and start on chapter 11. Chapter 11 is all on chi-squared and on categorical distributions. So first thing we're going to look at is some inference testing. There are three different tests that we're going to do with this one. This is the first of three. So this is what we call the chi-squared goodness of fit test. So we're just going to talk about Oops Very Captain Crunch. Captain Crunch is one of my husband's favorite cereal. So I thought I'd make an example with this one. And the company that makes it is the Quaker Company. And the Quaker Company claims that the distribution of berries is 40% purple, 20% blue, 20% red, and 20% green. And what we want to know is that a true statement? So what we did is we opened up a box and we grabbed some Oops Berry out, and we had 551 total berries. And we found that we separated them by color and found that 222 are purple, 109 are blue, 130 were red, and 90 were green. So what we want to know is that going to be what equivalent to what the company has claimed that it should be? So if you haven't printed this out yet, you may want to go ahead and pause the video here and go ahead and print this and the chi-square table. They can both be found in the modules. That way you'll have some paper to take notes on and you'll be able to follow along. The chi-squared is not any different from our other significance test in the fact that we start with the hypothesis that the claim is true. So what they're telling us is true. Where it is different is that instead of us writing it in symbol notation, we actually write it as words. Because if you look at our actual hypothesis or our actual problem up here, you can see we've got all these percentages. So we would have to do symbol notation for all of these values. So it's just much easier for us to go ahead and write this in words. We're going to go ahead and write this claim down. So the claim is that 40% are purple, 20% are blue, 20% are red, 20% are green. So that's basically what we state. We state our HO is that the claim distribution of Oops Berry is true. Well, then that would make our HA that the claim distribution of Oops Berry is not true. So the claimed distribution of Oops Berry is not true. Because we know it's got to be one of the two. Now, what should happen if the claim is correct? What should we have gotten? So we need to actually calculate those values. So we had 551 berries. So we need to figure out how many should we have gotten. So I'm going to ask you to go ahead and pause the video and think about that for a second. See if you can come up with what we should have expected or what should have happened if the claim was actually true. So let's check your answers against mine. If you can see the purple, we should have gotten 220.4. Blue was 110.2, red 110.2, and green 110.2. So how did we actually get those values? Well, we know that we had a total of 551 berries. And we know that for each one of these, there was a proportion or a probability of us having those. So the proportion for purple was 40%, and blue was 20%, red was 20%, and green was 20%. So if I need to know how many I should have got, well, it's basically just taking that proportion or that P and multiplying it by our N, which we've done before, N times P. So you see that's kind of a little bit like a mean. So we are going to go ahead and keep those decimals. Even though we know that you can't have like half a berry, we are going to go ahead and keep the decimals because it's working kind of like our mean. So this is a little bit like calculating our large counts. Now we know that we're going to have to do this for this N times P for each one. So we're going to put a little PI there because that counts for each one of these that we do. So we're going to go ahead and we've got our observed values, we've got our expected values. So I want you to go ahead and pause the video and I want you to go ahead and fill in the table and see if you can calculate all of these different rows. So I'll let you go ahead and check your values and see if they match what I have. And you can see that I added up that last column and I came up with about 7.284. You should be pretty close to that. You may be off just a little bit from rounding, or we may have, rounded differently or something along that lines. But this test statistic, well, what we're doing right now is chi-squared. So this test statistic right here is what we call our chi-squared test stat. And how we calculate that is pretty easy. We take our observed value minus our expected value. We square it. We divided it by our expected. And then we take the sum of that. So we're going to use our little summation notation right there. And that's how we actually calculate that chi-squared test statistic. Ideally, in a full test, we would be converting that test statistic to get that p-value. The problem doesn't ask us to do that in this case, but we're going to go ahead and I'll show you how to do it. So if we were using a t-test stat, we would just go to the t-table. But obviously, this isn't a t-test stat. This is a chi-squared test stat. So we got to go to a different table. So if you look in your packet or if you printed one off, you'll see that we do have a chi-squared table, and it looks something like this. Now, if you notice, we've got degrees of freedom, and then that tail probability is on the side. You can see it goes on quite a bit. So it all depends upon what our degrees of freedom are. Now, our degrees of freedom are calculated slightly different with chi than they are with our t-test stat. So with our chi-squared distribution, we calculate our degrees of freedom by taking the number of categories that we have minus 1. So our degrees of freedom, I'm going to write that up here. Degrees of freedom is equal to your categories minus 1. Well, how many categories do we have? We have 1, 2, 3, 4. So our degrees of freedom in this case is going to be 4 minus 1, which is 3. So our degrees of freedom are 3. So our test stat is 7.284. Degrees of freedom are 3. So let's go ahead and go back to the table. And we're going to go to degrees of freedom of 3. And we're looking for a value that is close to that 7.1. 7.28. I apologize. 7.28. So if you look at this, okay, so it's right here. So we know that our p-value is somewhere between that 10% and that 5%. We know then that our p-value is somewhere between 0.05, it's less than our p-value, which is less than 0.10. So our p-value is somewhere in that range. Now we can get the exact value by using the calculator, and I'll show you how to do that a little bit later, but let's go ahead and finish the problem. All right, so what value would we get for the test statistic if our sample was very close to what was expected? Well, if you think about it, that value should be really super close to 0. So it should be close to 0. Why? Well, how did we get the test statistic? To find that test statistic, we do that observed minus the expected. And if we're getting if our observation is close to what was expected, well, those two values should be a number that's relatively close to 0. Now, so it should be close to 0 because the observed minus the expected. All right. Now, what value would we get for our test statistic if our sample was far from what is expected? Well, in this case, it should just be some value that is relatively large. Here again, why? Because we're doing that observed minus that expected. And the further away that observed is from the expected, the larger our test stat is going to be. So this one should be a large number. Because the observed will be far away. Okay, so our last question, what color berry has an observed value that's farthest from the expected? What does it mean and what effect does it have on the test statistic? So let's look back up at our table. Which one of these berries had the furthest observed from what it was expected? And it looks like we're looking at these values, well, that would be the green. All right, the green was 20.2. So it was the furthest. Red was really close, but green was just a little bit. So now what does that mean and how does it affect the test statistic? Well, it means that it's going to have the greatest pull on the test statistic when it's calculated. But you can see those values, those are the higher values. So it means that this one was the furthest off, so to speak, than the other ones were. Followed a close second by that red. To wrap this up and look at the big ideas of this section so far. So we know that our important ideas here start with our hypotheses. And we know that the hypothesis is that the claim distribution, whatever the context is true. And then our HA is that the claim distribution, whatever the context is not true. Then to find our expected counts, we know that we take the sample size, whatever that may be, and we multiply it by that proportion or that percentage that they give us. And that's going to give us all of our expected values. Now to find the test stat, we do our observed minus our expected squared, and we divide it by that expected. Then we take the summation and add all of those up. So that gives us our chi squared test stat. We know that our degrees of freedom then is going to be the number of categories we have minus 1. So in our case, it was 4 minus 1, 3. And then to find that p-value, we can go to the chi-square table, or now here's that calculator section, and we'll do a little bit more work on this a little later. But if you go under your distributions menu, under the stats menu, distributions, you should see a chi-squared CDF, and you should be able to put your lower value, your upper value, and then your degrees of freedom in there. And it should give you what that p-value is. Now that lower value most of the time is going to be your chi-squared test stat. So it should help you get an exact value. So there's a practice problem that follows. I want you to pause the video, and then I want you to come back, and we'll work through the practice and see if you've got it correct. All right, so let's go through the problem. Carrie made a 6-sided dice in her ceramics class and rolled it 90 times to test if each side was equally likely to show up. The table summarizes the outcome of her 90 rolls. So we're going to state our hypothesis. Well, HO would be that the claimed distribution of 1/6 probability for each roll is true. So that dice is a fair die. HA would be that the claimed distribution of 1/6 probability for each roll is not true. So that means the dice is not fair. So we're going to calculate the expected counts. Because the probability is the same for each one of the outcomes, we can just do 1/6 times 90, which is 15. So each of the expected counts should be 15. So now if we calculate our chi-square test stat, we're going to take our observed minus our expected divided by our expected. So you can see in this case, I didn't write all of them out. Generally speaking, if you just start a couple and you do the first two and the last one with your little dots in between, you can generally get away without having to write all of them out. And then we give a total. Our total is 14.4. So what degrees of freedom should we use? Well, there were 6 different numbers that could happen. So 6 minus 1 is 5. So now use table C to find the p-value. What conclusion would you make? Well, the p-value is somewhere between 0.01 and 0.02. So we know that in both cases that p-value is less than a normal level of significance of 5% or 0.05. So we would reject the HO. We have convincing evidence that the dice is not fair. So next video that we do, we'll get into actually making this a formal hypothesis test. We'll use our format, and I'll show you some of the calculator stuff, and we'll get it done. So we'll see you then. Bye-bye.